This video will discuss molecular dynamics for chemical systems. Okay, so a couple videos ago we mentioned for ensemble properties that one way to get various properties of a molecular system is to, instead of integrating the contributions to that property over all of the different spatial configurations that are possible, is instead we could calculate an average of that property over a large value of time. So we could simulate the system for some amount of time and then derive average properties from that. So that type of procedure is called molecular dynamics, or calculating properties by propagating the system through time and getting a time average of various values. Okay, so the way we're going to do this using the kind of typical machinery that's used is classical mechanics. And classical mechanics and time means Newton's laws. So we're starting with a conservative time-independent potential energy function. Namely, that potential energy function is typically going to be molecular mechanics, the types of energy functions from the previous chapter, force field types of methods, usually because we're usually using systems which are too large for quantum mechanics-based systems, as we'll see in the future. Okay, so if we're using hundreds or thousands or tens of thousands of atoms, we have to use molecular mechanics. So Newton's laws means F equals ma. So the acceleration of any of our individual particles is related to the force that they feel, and it's proportional to, and the proportionality constant is the mass. Okay, so what does this mean for our various components? So this means that the negative gradient of the energy function, so negative del V, which is our force, is going to be equal to mass times acceleration. Acceleration is the second derivative of the spatial coordinate with respect to time, so a equals d squared x dt squared. It also equals the first derivative of velocity, but m times a is the first derivative of momentum. So that equals, we might say, dp dt. So this is the kind of equation that we're solving there, which is what it reduces to for a conservative time-independent potential energy function. Okay, so we can break this down further still because we know what this gradient is. This gradient is a bunch of various spatial derivatives. So our force is equal to the negative gradient, which is going to be sum over all of our dimensions, if we have n dimensions, of minus partial derivative of potential energy with respect to that individual coordinate, so we'll call that xi, even though that's not necessarily an x, could be y or z as well. So that's the force, and that is going to equal the acceleration, which, as we said, for summing over all of those dimensions, is going to be the second derivative of x with respect to time, or as we also said, the derivative of momentum in that dimension, so derivative of the x momentum with respect to time. So these all correspond. For all n of these dimensions, you get a different equation to solve. But what this ends up coming out to is for every individual dimension, the function that we are solving is that the way that the momentum changes over time is equal to the negative partial derivative of the potential energy with respect to that coordinate that that momentum belongs to. So we want to solve this for all 3n dimensions of our molecule or of our molecular system. Okay, so once more, we could directly integrate this if this was a simple function, and we can get lucky for a few simple functions that you can directly integrate this partial differential equation. But in general, you can't unless you get super lucky. So what you have to do instead is solve it numerically. As we do so many things in computational chemistry, the numerical solution is what we must live with. Okay, so molecular dynamics is a specific algorithm for solving this equation for how we're propagating our system through time, and we're getting a classical Newtonian trajectory of a set of points of our coordinates at various points in time that we're then going to average over for some property of interest. Okay, so the first thing we're going to do, we're going to assign initial values for our coordinates and for our momenta. So remember, in case we don't remember that specific general physics lesson, is that P equals, or let's say Px equals mVx equals m dx dt. So momentum is the velocity, which is the first derivative of x with respect to time, times mass. So we have to assign some initial set of coordinates, positions, and our momentum. Okay, so once we have done that, what we're going to do is compute various properties of interest. So we'll compute our energy. So we'll compute V of x. We'll compute the gradient of the energy. Any other properties of interest, ... Okay, then the next thing that we will do is we will update the x, that xn plus 1 equals xn plus 1 over m Pn delta t. Okay, so it's momentum mass times velocity, which is mass times change in position with respect to time, multiplying times dt gets rid of this denominator, dividing by mass gets rid of this m. So what we're left with is it's x, the next x equals the previous x plus a change in x dx. Okay, so that's our updating of our positions. And we're going to update our momenta, so update the velocities, update the momenta, equals the current value of those things, plus minus partial derivative of v with respect to the position times delta t. Okay, so the force is equal to mass times acceleration. The negative gradient is equal to the change in the momentum over time. So the change in the momentum over time times time is the change in the momentum. So going from our current momentum to the next times momentum is the change in the momentum. All right, so we've updated that. So now what do we do? So all that's left to do is repeat until we've reached our specified time. So till t is greater than the final t. So we start at t naught, we go all the way to tf. We've specified how much time we want to simulate, whether that's a femtosecond, picosecond, nanosecond, microsecond, millisecond, full second, what have you. All right, and then once we have done that, then we will compute desired properties. Maybe we want the radial distribution function of something. Maybe we want an average bond length. Maybe we want the average energy. Maybe we want the, this, that, or the other thing, average dipole moment. Who knows? But whatever properties we have, we can average over all the trajectories and all the time points that we have there. Okay, so what are some of the nuances that are going to go into this? So the number one, which might be the most glaring here, is this delta t. So this delta t is called the time step. And typically the time step you're using in molecular dynamics is around 1-ish femtoseconds, which is 10 to the minus 15th seconds. So why do you have to use that? So the time step that you can use is constrained by what is the highest frequency motion that you have in your system. Typically the highest frequency motion you have in your system is the vibrations of individual chemical bonds. So the vibration of, let's say like an HF molecule of a CC bond and something, the quickest vibrations, typically those with hydrogens, are occurring on the time of around 10 femtoseconds. So you need to be around 5 to 10 times quicker than that. So that's your constraint. If you're doing molecular dynamics on things where you don't have vibrations that are that fast, where you have larger time scale motions, you can get away with a larger time step. In situations where things happen faster, you have to do an even smaller time step. It's all constrained by what are the fastest motions that occur in your system. Okay, and then there's the total time. So the total time you want to simulate really depends on the goal of whatever simulation you're doing. So it depends on what kind of properties you have interest in. So things like, let me write that better. Depends on goal. So things like bond or angle vibrations, those might be something between a femtosecond to a picosecond, 10 to the minus 15 to 10 to the minus 12 seconds. Similarly, something like a dihedral rotation might be on that same kind of thing, like the motion of the hydrogens around the dihedral in ethane. Something like a conformer motion, like maybe you have a small peptide that's changing from one conformation to the other, a very small peptide. That'd be something like a picosecond to a nanosecond, 10 to the minus 12 to 10 to the minus 9th seconds. Something like a peptide folding, or some kind of bulk diffusion, some type of slower event like that. That could be anywhere from, say, like a nanosecond to a microsecond, minus 9th to 10 to the minus 6th. And then larger scale macroscopic results, things like protein folding and other large biological processes. Those are the things that the longest simulations generally occur, and those are things that are on the kind of microsecond to full second time scales. So the largest molecular dynamics simulations done in the world are up to millions of atoms, and the longest ones are up to hundreds or even hundreds of milliseconds or even a full second now. But basically you can simulate these properties for long enough to get whatever process of interest you're interested in. The longest ones are typically interested in protein folding, and the largest ones are typically interested in simulating systems with lots of atoms. But this is molecular dynamics, and this is a very common technique for lots of simulations in biophysics, biological systems, and biochemical simulations.